Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 52. It's on torque. Torque is simply the product of the force, which is perpendicular to the lever arm, and this only works in rotational motion. So what is rotational motion? Imagine that we've got a wrench that's sitting here, and I've marked the center of gravity. And so let's say it's just sitting in space to make this easier, and let's say I apply a force right at that center of gravity. What we're getting is linear, or we call that translational motion. We apply a force in one direction, and we're seeing an acceleration in that direction. Let's say I do the same thing, but now I'm going to do it off-center. So I'm going to apply a force not at the center of gravity, and watch what we get. We get two forms of motion. We're getting that translational motion, but we're also getting rotational motion. And it's hard to separate those two. And so an easy way to look at rotational motion is to pin it down. So now I've got the same thing. We've got the wrench, but now it's centered around this nut on one side. And so this isn't moving, so it's going to rotate around that point. Now let me apply that same force on one direction, and now we're just getting that rotational motion. Let me return the wrench for a second, and we can start to talk about what torque is. And so this is going to be the lever arm. The lever arm is going to go from this point in the middle, that axis of rotation. It's going to go out from that. It's perpendicular to that axis of rotation. And it's just like a lever that you would use as a simple machine. And then we're applying a force perpendicular to that lever arm. And so what is torque? We're multiplying these two values. We're multiplying the force that we apply perpendicular to the lever times the lever arm itself. And so it's two things, and the units aren't just going to be newtons, it's going to be Newton meters. And so in a rotational system like this, where we have an axis of rotation, what is torque? It's simply the product of that lever arm, which is going to be a vector, and has to be perpendicular to that axis of rotation. Again, the axis of rotation is coming straight at us through the middle. And we're going to multiply that times the force. The force has to be perpendicular to that lever arm. And so if we multiply those two values, then we're going to have ourselves a torque. And this is our equation right here. Tau, which stands for torque, is equal to that lever arm, perpendicular, and then that force. And so if we have a system that's not moving, like our rotational system is not moving anymore, we know that all those forces must be balanced. In other words, all the torques must be balanced. And so the net torque on a balanced system is equal to 0. Have you ever noticed that a door will always have the doorknob on the outside or far away from the hinge? Well, the reason that is just deals with torque. And so what I have here is the door itself. This is the door hinge right here. And here's the doorknob on the outside. And so if I apply a force out here, what am I going to get? Torque. We've got the lever arm, and then we're applying a force perpendicular. And so we're going to get an acceleration or a rotational acceleration like that. What happens if I apply a greater force? What am I going to have? I'm going to have a greater torque. And so we're going to see a faster acceleration like that. What happens if I take that smaller force, however, and move it to the inside? What happens if I put the doorknob on the inside of the door? If I try to pull on it with that small force, nothing will happen. In other words, I've decreased that torque so much since I've decreased that lever arm that I wouldn't have enough torque to open that door. And so that lever arm distance is incredibly important. Just like a lever in a lever system, it's giving us a mechanical advantage to open up that door. So in torque, we're applying that lever arm times the force. That's how we calculate the torque. And the equation looks like this. Tau is equal to R perpendicular F. And so let's add some numbers in here, and I'll show you how to calculate that. Let's say the doorknob is 75 centimeters from the hinge, and we apply a 6.7 Newton force. What's going to be our torque in this situation? Well, I'm going to plug in those values. Again, I had to convert these centimeters into meters. We have to use SI units. And now I simply multiply those values. What are my units? It's now in Newton meters. You can see I have too many significant digits, and so we would get a 5.0 Newton meter torque if the doorknob is at the outside. Now watch what happens if we move it 15 centimeters from the hinge. Watch what happens to our torque. Again, the force is going to be the same, but now we're going to get a 1.0 Newton meter torque. It's 1/5 it was before, which isn't surprising because the lever arm is now 1/5 what it was before. Let's take a second to look at a balance system, and a seesaw or a teeter-totter is a great example of that. We have the axis of rotation right here in the middle, and we can have a lever arm on this side and a lever arm on the other side. So what we can do is we can apply a torque on one side and a torque on the other side. And if those torques are equal, then we're going to have a balanced system where you shouldn't see any movement. And so watch what happens when I remove the supports. Since the torque is the same on either side, nothing happens. Let me apply a 5 kilogram weight on either side. If I remove the supports, it's totally balanced. Torque is equal on either side. Let's say I add a 10 kilogram weight to the right side and now remove the supports. What happens? Well, we've got greater torque on the right side, and so we're getting rotational motion in that direction. Now, a good question I might ask you is, where could I move that 5 kilogram mass on the left side so the torque on the left equals the torque on the right? How could I balance this system out? Well, if we look at our equations, again, it's simply the product of the lever arm times the force. And so if I throw in some values here and set them equal to each other, on the left side we have the unknown lever distance times that 50 Newton force. Where do I get the 50 Newton force? I'm simply taking 5 kilograms times about 10 for the acceleration due to gravity. So it's a 50 Newton force down on that side. On the other side, it's going to be a 100 Newton force. So I could solve for this. We'd have a torque of 400 Newton meters on the right side. And so to solve for that, we should have a distance on the left side equal to 8 meters. And so if I take that 5 kilogram mass, move it out to 8 meters, what are we going to get? A balanced system. The torque on either side is going to be exactly the same. And so did you learn the relationship between a force and a torque? Again, we have to multiply the force times that lever arm. Do you see what happens when we apply different forces? We increase the torque. Or what happens if we move that force in? We're decreasing the torque because we're decreasing the lever arm. Can you design an experiment that would allow you to kind of manipulate these balanced forces? Again, we used a teeter-totter to do that. And finally, can you calculate torque in a two-dimensional system like this? I hope so, and I hope that was helpful.